Welcome to the architectural side of networking, where we build the digital equivalent of roads, bridges, and traffic lights. If you've ever played with Legos, you're already halfway to understanding network infrastructure. Except, instead of stepping on painful plastic blocks, you'll be stepping through the building blocks of modern connectivity. We'll explore how switches, routers, and cables come together like a perfectly orchestrated symphony, though sometimes it feels more like a garage band's first practice. In this video, we'll peel back the layers of the typical business network, examining everything from cables that carry our data to the advanced traffic management devices that keep packets flowing smoothly. Our goal is to give you a comprehensive understanding of the hardware involved so you can make more informed decisions when it comes to optimizing performance and security. Let's start with the physical layer. This is cabling. Then we'll build our way up through switches and routers that form the control plane of the network. Along the way, we'll highlight key concepts like VLANs for segmentation, routing protocols that choose the best path, and firewall evolutions for perimeter defense. Finally, we'll touch on some of the specialized devices used for load balancing, caching, and virtualizing network functions in the cloud era. By the end, you'll have a solid grasp on the equipment and technologies that power our digital infrastructure from end to end. Whether you're a network engineer looking to design more resilient architectures, a software developer trying to optimize application delivery, or a business stakeholder aiming to maximize uptime and security, this knowledge will serve you well. So let's begin our journey at the foundation, the physical media that carries all the zeros and ones. At the lowest layer of our network model, we have the cabling that physically connects devices. Choosing the right type of cable is crucial. It determines the speed, capacity, and reach of the network segments it serves. In the world of wired networking, copper and fiber are king. Copper cabling typically takes the form of twisted pair Ethernet. It's cost-effective and easy to deploy for connecting end devices or linking switches in the same room or building. But not all copper is created equal. Ethernet standards like Cat5, Cat6, and Cat8 offer varying grades of performance in terms of bandwidth and distance. For example, Cat6 supports data rates of up to 10 gigabits for cable runs under 55 meters, while Cat8 ratchets that up to 25 or even 40 gig, although only for shorter 30-meter spans. So when designing a wired LAN, it's important to know the requirements of the devices and applications that will be using the network, and choose cabling to match. Cat6a is a sweet spot for many new builds, offering 10 gig speeds up to a full 100 meters. But for longer runs between cities, it's time to call on the heavy hitter of the cabling world, fiber optic. Rather than carrying electrical impulses, fiber uses pulses of light to carry data at incredible speeds over vast distances. Single-mode fiber with its skinny 8-micron core can send 10 gig signals over distances measured in kilometers rather than meters. That reach makes fiber the obvious choice for high-speed campus backbones, long-haul internet links, and undersea cables. And with none of the electromagnetic interference that can plague copper in noisy environments, it's also great for networks in factories or industrial sites. So your cabling infrastructure is really the foundation on which the rest of your network is built. Choosing wisely here can make a huge difference in performance and reliability down the road. With the right mix of copper and fiber in place, it's time to look at the devices that turn the passive cabling into an active network. The most basic of these are repeaters, simple boxes that do nothing but amplify and retransmit incoming electrical signals in order to extend cabling reach between devices. You'll find these in spots where cable lengths exceed specs, but fiber hasn't yet taken over. One step up from repeaters, hubs, were once the glue that held LANs together. By replicating incoming data to all connected ports, hubs allowed multiple devices to communicate over shared Ethernet. But because they created a single collision domain where every node competes for airtime, hubs have largely given way to more intelligent switching. To link it all together, we have the Network Interface Card, or NIC. The NIC serves as a translator between a computer and the network, converting layer 2 frames into electrical or optical signals and back again. Gigabit or 10 gig Ethernet NICs are now standard issue in servers, PCs, and laptops. Examples include 25, 40, and 100 gig Ethernet on newer servers. So now, we have a bunch of devices linked together with high-speed cabling, with NICs letting them speak the same low-level language. But to really scale out a LAN, we need more structure and intelligence. For that, it's time to explore the world of switches and routers. If cables are the roads of our network and NICs are the driveway, then switches and routers are the traffic lights and highway interchanges that let us scale from small towns to the whole wide world. Let's start with switches, as they really are the core building blocks of modern Ethernet networks. Switches operate at layer 2 on our network model, dealing with MAC addresses to determine where to forward Ethernet frames. Unlike hubs, switches maintain a table to map port numbers to the addresses of connected devices. This lets them intelligently send frames only to the intended recipients rather than broadcasting to everyone. By segmenting collision domains, switches bring major improvements in terms of bandwidth efficiency and performance. Each device connected to a switch can operate at full duplex, meaning it can send and receive data simultaneously without having to wait its turn. That's a huge leap from hubs and shared Ethernet. But switches alone aren't enough once our network grows beyond a single LAN. We need a way to break up broadcast domains and contain traffic at higher level. And that's where virtual LANs or VLANs come in. By tagging frames with a VLAN identifier, switches can carve up a single physical network into multiple logical segments. Devices in a VLAN can only talk directly to other devices in that same VLAN, no matter where they're plugged in physically. But because VLAN membership is defined in software, these logical topologies can be much more flexible than physical wiring. The benefits are numerous. By isolating different classes of traffic like IP phones, wireless access points, and servers, we can boost performance while tightening security. Imagine you're the sysadmin at a university. You might put student computers in one VLAN, faculty and staff machines in another, and security cameras in a third. They're all sharing the same switches and fiber, but it's like they're living in different worlds. Of course, sometimes we do need to jump between those worlds. If you're on a student VLAN, but you need to hit a file server or printer on the faculty and staff side, we're going to need some help from layer 3, and that's where routers come in. Routers connect different IP networks together, making decisions on where to send packets based on their IP addresses. There are on-ramps for the layer 3 highway, letting us span the gaps between VLANs, subnets, campuses, and ISPs. While switches mostly just learn MAC addresses, routers have to be smarter. They use protocols like OSPF to discover and calculate the best path to every corner of the network. Link state data gets churned through by an algorithm to build a network topology map, letting each router make its own decisions on where to forward traffic next. But there's a lot more of the internet out there beyond our local networks. We need even more powerful protocols to tie it all together. That's where BGP comes in. The Border Gateway Protocol allows huge networks owned by different companies and countries to share routing information. As a path vector protocol, BGP is less concerned with optimizing every single hop and more focused on finding reliable end-to-end reachability. BGP routers at the edge of big autonomous systems exchange route advertisement, apply policy filters, and decide which way to prefer. The result is a sprawling interconnected web of networks we call the public internet. So if OSPF is like mapping out the roads in a single city, BGP is deciding which interstates and flight paths connect the whole world. As we've built larger and more complex networks, we've had to evolve our perimeter defenses as well. That brings us to firewalls. Firewalls are our border patrol agents, deciding which traffic gets in and out of our trusted networks based on a set of rules. Early packet filtering firewalls made the call based purely on IP addresses, port numbers, and protocols. But that's a pretty coarse approach, sort of like deciding who gets into the club based purely on how they're dressed. Enter the stateful firewall, which keeps track of actual connections and uses that context to spot shady behavior. By watching the back and forth flow of packets, these firewalls can catch the kinds of scans and probes that often precede an attack. It's like noticing that a certain group of people keeps circling the block and peeking in the windows before deciding to let them in the door. Next generation firewalls take it even further, adding deep packet inspection to actually examine the contents of packets for threats. They're application aware, so they can tell the difference between normal web browsing and a suspicious executable download. And they roll other defenses like intrusion prevention, malware scanning, and all of that into a single unified platform. But even with all of these advanced security devices protecting our perimeter, we still need a way to securely connect different sites across the untrusted internet. And that's where VPNs and WAN optimization tech like SD-WAN come in. By encrypting traffic and logically bonding multiple links into a resilient overlay fabric, we can build global private networks without the cost of dedicated MPLS circuits. Finally, let's zoom out beyond the LAN to look at the devices that connect us to our ISPs and the larger internet. At the edge of most access networks, you'll find a cable, DSL, or fiber modem linking the LAN router to the carrier's WAN infrastructure. Cable and DSL modems operate over the existing coax and phone wiring, while fiber links use dedicated optical lines to maximize speed and distance. In each case, the modem is responsible for modulating between Ethernet frames and the Layer 1 signaling required for the access network, be it DOCSIS for cable, DSL for phone lines, or PON for fiber. This is the digital to analog conversion that lets our packets ride over a provider's aggregation and core routers on their way out to the big internet. So, we've seen how NICs, switches, routers, firewalls, and modems all work together to create the complex topologies of modern enterprise networks. But as virtualization and cloud have changed the way we build application, they're also revolutionizing the way we think about network infrastructure. And that brings us to the realm of software-defined networking and advanced network services. In our journey through the physical network infrastructure, we've traced the paths of data from its source in a server or end-user device, across switches and routers, through firewalls and VPNs, all the way out to the internet and back again. But in the era of virtualization and cloud, more and more of that infrastructure is moving from dedicated hardware to software running on general-purpose servers. The trend started in the data center with the rise of virtual switches. Products like VMware's vSwitch and the open-source Open vSwitch turned a single physical host into a complex Layer 2 fabric, linking local VMs to each other and the outside world. By abstracting switches into software, virtual switches enable more agile provisioning and management of networks in a highly dynamic virtualized environment. Multi-tenant data centers and hybrid clouds would be a nightmare to reconfigure at the physical layer. But with virtual switches, we can define and modify network microsegmentation with just a few mouse clicks. As SDN has matured, we've seen control of virtual and physical switches converge under the reign of centralized SDN controllers like VMware NSX and Cisco ACI. These platforms act as the single source of truth for network state, applying a consistent set of policies and letting us treat the whole data center like one big fabric. But switches aren't the only devices feeling the winds of virtualization. Routing and firewalling have also been abstracted into the world of ones and zeros, with virtual routers and virtual firewall appliances bringing Layer 3 smarts into the hypervisor. For example, most public cloud platforms now offer a managed Layer 3 routing service to interconnect virtual private clouds and on-premise networks. And the virtualized next-generation firewalls can secure east-west traffic between application tiers or replicated databases, without the old model of backhauling everything through a physical appliance. But it's not just about doing the same old network in software form. Advanced devices like load balancers and application delivery controllers have evolved to meet the needs of modern application architectures. Historically, load balancers were often a pair of dedicated hardware appliances serving as the gateway to a farm of web or application servers. Their job was to distribute incoming requests evenly across the pool of servers, so that no one single node would be overwhelmed. Simple algorithms like round-robin or least connections did the trick. But as applications have become more complex and containers have supplanted VMs as the unit of deployment, load balancers needed to evolve. Enter the Application Delivery Controller, or ADC. An ADC is like a load balancer on steroids. Sure, it still does the basic job of distributing traffic across a pool of servers, but it also takes a much deeper look at the application behavior and makes smarter decisions to optimize performance. For example, an ADC can inspect HTTP headers and route requests based on URL or cookie data. So a request for a static image or style sheet could be sent to a pool of caching servers, while a dynamic request requiring authentication might go directly to an application server. ADCs can also improve application performance by offloading compute-intensive tasks like SSL termination, caching, and compression. By handling these functions in the ADC, we can free up cycles on the application servers to focus on business logic. Because they sit in the critical path of application traffic, ADCs are a natural enforcement point for web application firewalls and DDoS defense. They can inspect incoming requests for signs of SQL injection or cross-site scripting attacks and block them before they ever reach a vulnerable server. But perhaps the most important aspect of modern ADCs is their deep integration with the application platforms and management frameworks. Rather than being an island unto itself, the ADC becomes an active participant in the automated application delivery pipeline. Developers can define application routing rules and load balancing policies as code, right alongside the application itself. And the ADC can pull from the application monitoring metrics or third-party threat intelligence to dynamically adapt its behavior in real time. The result is an application delivery network that's more agile, more responsive, and more secure. But even with this software-defined approach, sometimes we still need to be able to inspect and control traffic at a more granular level. And that's where next-generation networking services like encrypted traffic analytics come in. One of the dirty secrets of network security is that we have largely been flying blind when it comes to encrypted traffic. Sure, we can block traffic to known bad IP addresses or domains at the firewall, but once traffic is encrypted with SSL or TLS, we lose a lot of visibility. That's a problem because encryption is becoming the default for more and more applications, even ones we wouldn't normally think of as sensitive. In fact, some studies suggest that up to 70% of all web traffic is now encrypted. Encrypted traffic analysis, or ETA, uses advanced machine learning algorithms to spot the telltale signs of malware or data exfiltration, even when the packets themselves are encrypted. By training on massive data sets of normal and malicious encrypted traffic flows, ETA can build behavioral models and detect anomalies and raise alarms. So rather than just blindly blocking all encrypted traffic or letting it through and hoping for the best, we can now apply a more nuanced approach to balance security and performance. We've come to the issue of actually enforcing all these advanced network and security policies across a highly distributed and heterogeneous environment. And that's where automation and orchestration tools like Ansible, Puppet, and Chef come into play. In the past, network operators spent countless hours manually configuring switches, routers, and firewalls through a command line interface or a clunky web GUI. But in the world of infrastructure as code, we can define our desired network state in a declarative, machine-readable format and let the automation handle the rest. Want to spin up a new virtual network segment for an application test environment? No problem. Just update the playbook and let Ansible configure the relevant switches and routers. Need to roll out new security policy across all your firewalls and ADCs? Chef can handle that in a matter of minutes, with full auditing and rollback capabilities. And because these automation tools are all based on open source projects with vibrant user communities, it's easy to find pre-built modules and integrations for just about any network gear out there. That means less time spent on low-level scripting and more time focusing on high-level design and architecture. In this video, we have taken a look at the physical components of network infrastructure, from the cabling and interface cards that form the foundation to the switches and routers that act as the control plane, all the way up to application delivery controllers and firewalls that protect and optimize our applications. We've seen how the rise of virtualization and cloud computing has fundamentally changed the way we design, deploy, and manage network infrastructure. No longer are we bound by the physical limitations of custom-built hardware appliances. Instead, we can now treat the network as a flexible, programmable fabric defined and controlled through software. But this shift to software-defined networking and infrastructure as code isn't just about doing things faster and cheaper. It's about fundamentally rethinking the role of the network in modern enterprise. In a world where applications are the lifeblood of businesses, the network can no longer afford to be a static utility, an afterthought in a grand scheme of IT. Instead, it must become an active partner in the application delivery process, able to adapt and evolve in real time to meet the changing needs of business. That means network engineers must also evolve. We can no longer think in terms of individual devices or protocols, focusing on low-level configuration and troubleshooting. Instead, we must become software-savvy architects, able to design and orchestrate complex application delivery networks that span multiple clouds and data centers. And we must embrace automation and continuous delivery, so that the network can keep pace with the speed of modern application deployment. But perhaps most importantly, we must never lose sight of the fundamentals. Even in a world of software-defined everything, the physical infrastructure still matters. The right choice of cabling, the right network design, and the right security stance, these things are just as critical as ever. So as we move into this brave new world of programmable networks and infrastructure as code, let us not forget the lessons of the past. Let us build on the solid foundation of switching, routing, and firewalling that has served us well for decades. And let us use the power of software and automation to make that foundation even stronger, more agile, and more secure. It's all about delivering applications and services that drive businesses forward. That's the true measure of success for any network, and it's the goal of what we should all strive for. Well done with mastering the structural backbone of networking. Now you know enough about infrastructure to be dangerous, or at least dangerous enough to stop blaming DNS for everything, though it's still usually DNS. In our next chapter, we'll dive into network operations, where we will learn to keep the digital orchestra playing harmoniously. Remember, good infrastructure is like a good referee. It works so well, you barely notice it's there.